Hello students, welcome to this video lecture on System of Particles and Rotational Motion Part 4. This chapter is given in chapter number 7 of class 11 for physics. In this part, we will study about moment of inertia, theorem of perpendicular axis and theorem of parallel axis. In this section, we will answer the basic question that what is the analog of mass in rotational motion? We shall attempt to answer this question in this section and keep our discussions very simple. We shall consider first the rotation about a fixed axis only. Let us try to get an expression for the kinetic energy and rotating body. This is also a bit lengthy discussion and you have to listen to my lecture very attentively because some theory part or text part I am skipping and only explaining orally. However, important points are given in the form of short notes. Hence, I request you to note down all important points. Welcome you once again. Moment of inertia. Moment of inertia plays the same role in rotational motion as mass. Underline the word mass plays in linear motion. It is the property of a body due to which it opposes any change in state of rest or uniform rotation. Moment of inertia is represented by a symbol capital I and its relationship with perpendicular distance and mass is given by I is equal to m into r square, where m is the mass of the particle and r is the distance of the particle from rotational axis. Please underline rotational axis. Moment of inertia of a body made up of number of particles, that is discrete distribution, is given by the relation capital I is equal to m1 into r1 square plus m2 into r2 square plus m3 into r3 square. Here r1, r2 and r3 are the distances of the respective particles, number of particles from the rotational axis, and mass m1, m2, m3 is the mass of respective particles, different particles. Moment of inertia of a continuous distribution of the mass, that is instead of discrete distribution, if the body is made up of continuous distribution of mass, then it is given by the relation di is equal to dmr square, or I is equal to integrating I is equal to r square into dm. Dimensions of moment of inertia are within square brackets m l square t to the power of 0. The SI unit of moment of inertia is kgs meter square. Moment of inertia depends on mass, distribution of mass, and on the position of the axis of rotation. Moment of inertia is a tensor quantity. Tensor quantity means a physical quantity which is neither vector nor scalar, similar to example stress on the material. Moment of inertia and kinetic energy. For a particle at a distance r from the axis, we know that the linear velocity is given by the relation Vi is equal to Ri into omega, where Vi is the linear velocity, and Ri is the distance of the particle, ith particle, and omega is the angular velocity. The kinetic energy of this particle, as we know, we have studied it in our previous videos. That is, kinetic energy of the ith particle is given by Ki is equal to half m1 v1 square, or we can say half mi ri square omega square, where mi is the mass of the particle. The total kinetic energy, capital K, of the body is then given by the sum of kinetic energies of all the individual particles. Therefore, applying the summation relations, we get capital K is equal to sigma I is equal to 1 to n of Ki. That is equal to half into half, we have taken half into sigma I is equal to 1 to n of mi ri square omega square. That is, using the relation kinetic energy is equal to half mv square. So V is r omega. So we have substituted the value of velocity in this relationship. Hence, n is the number of particles in the body. Note that omega is same for all the particles. Hence, taking omega sign outside the summation or integration sign, we get K is equal to half of omega square into sigma I is equal to 1 to n of mi ri square. We define a new parameter characterizing the rigid body called moment of inertia, which is given by the relationship I is equal to sigma I equals 1 to n of mi ri square. I will read this relationship, this equation once again, so that you can differentiate between capital I and small I. Capital I is the moment of inertia. Capital I is equal to sigma I is equal to 1. Small I is equal to 1 to n of mi and ri. I is the any small particle, discrete particles. Let it be equation 1. We define this again with this definition of inertia expressed in equation 1. We mention K is equal to, in this equation we put K is equal to half of omega square into capital I. Let it be equation 2. Note that the parameter I is independent of the magnitude of the angular velocity. It is the characteristics of the rigid body and the axis about which it rotates. Compare equation 2 with kinetic energy of a rotating body with the expression for the kinetic energy of a linear body. That is, when we say kinetic energy of a body in linear motion, that is translation motion, we know that kinetic energy capital K is equal to half mv square. Therefore, hence this m is the mass of the body and v is the velocity in this relationship equation. We have already noted analogy between angular velocity omega in respect of rotational motion about a fixed axis and linear velocity v, that is in respect of linear motion. It is then evident that the parameter moment of inertia capital I is the desired rotational analog of mass in linear motion. In rotation about a fixed axis, the moment of inertia plays a similar role as mass does in linear motion. Please note down. Let us calculate the moment of inertia of simple bodies. In the first case, we will consider a thin ring of radius capital R. This is the ring of radius capital R and its mass is capital M, and this ring is rotating about its own plane in its own plane with angular velocity omega. Each mass of the ring element is at a distance capital R, that is radius of the circle from the axis. This black color line is the axis, and the ring moves with a speed of r into omega. The kinetic energy is therefore given by capital K is equal to half of m into v square, where v is the linear velocity. And again, in terms of rotational motion, its kinetic energy is half of m into r square omega square, where omega is the angular velocity. Comparing, we get k is equal to half into I omega square. Here capital I is the moment of inertia. Therefore, we get I is equal to mr square for the ring. Next case, we will consider a rigid rod of negligible mass of length L with pair of small masses rotating about its axis through the center of mass perpendicular to the rod as shown in figure on the right hand side. So this is the rod, total rod. It has got its center C as its center. Therefore, the length on the left of C is L by 2, and the right hand side of C is also L by 2. Similarly, mass is M by 2 and M by 2 on either side respectively. Each mass m by 2 is at a distance of L by 2 from the axis. The moment of inertia of the masses is therefore given by the relation m by 2 into L by 2 whole square plus m by 2 into L by 2 whole square. Summing up, we get thus for the pair of masses rotating about its axis through the center of the mass perpendicular to the rod is given by the relation I is equal to m into L square by 4. This we obtained by summing up in the previous equation above. Radius of gyration. Radius of gyration of a body about a given axis is the perpendicular distance of a point from the axis, where if whole mass of the body were concentrated, the body shall have the same moment of inertia as it has with actual distribution of mass. When square of the radius of gyration is multiplied with the mass of the body, the relationship gives the moment of inertia of the body about the given axis. That is, moment of inertia capital I is equal to m into k square, or simplifying, k will equals square root of I by m. Examples of radius of gyration and moment of inertia will be displayed on the screen in the next slide. Please observe the table in the next slide very carefully. In this relationship above, K is called the radius of gyration. The length k is a geometric property of the body and axis of the rotation. It is called radius of gyration, given by the relation small k is equal to square root of r1 square plus r2 square plus etc 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 up to rn square divided by n, where r1 is the distance of the particle 1 and r2 is the distance of particle from the axis of rotation, and Rn is the distance of the particle from the axis of rotation. And since there are n number of particles, it is divided by n. Hence, small k is equal to r1 square plus r2 square plus etc etc up to rn divided by n. For a given body, inertia is constant, whereas moment of inertia is variable. Moment of inertia of some standard bodies and in different axes are shown in the table below. Here we have given in the first column the body, the type of body, like for example ring, a cylindrical shell as shown in the figure, and its axis of rotation is about an axis passing through the center of gravity. This is the center of gravity and perpendicular to the plane. So this is the plane of the ring and this axis is perpendicular to the plane. And the figure is shown here, and its moment of inertia is mr square. And its radius of gyration, small k, is r. Like this, we have given the moment of inertia, which is a function of axis of rotation and the type of body, as well as the radius of gyration in the table. Please go through it. Derivations are for the moment of inertia and radius of gyration is not included in the syllabus of NCERT physics for class 11. Maybe these relations you may have to derive in the higher classes. Please, for the time being, note down the moment of inertia and radius of gyration as well as the axis of rotation. The axis of rotation, you can see it is varying. It is passing through the center or about its diameter or about its tangential axis perpendicular to its own plane, and different cases are given here, and the moment of inertia is also given. Hence, small k is the radius of gyration, and observe from the table that moment of inertia, that is the column number 4, I is equal to, can be written as, we can write moment of inertia as I is equal to m of small k square, where small k has the dimensions of length. For a rod about the perpendicular axis at its midpoint, that k square is equal to L square by 12. This is the case. So here if you consider the thin rod, long rod about its perpendicular axis, this is the perpendicular axis, and its moment of inertia is given by ml square by 12, and its radius of gyration is L by square root of 12, that is square root of L square by 12. Similarly, another case For a circular disk of circular diameter about its diameter is r by 2. This is the case. Here the disk case is about its diameter is 1 by 4 mr square is the moment of inertia. Hence, the radius of gyration k is r by 2. Please note it. Theorems of perpendicular and parallel axes. There are two useful theorems relating to moment of inertia. We will first discuss the theorem of perpendicular axis and its simple application in working out the moment of inertia of some regular shaped bodies. Theorem of perpendicular axis. The theorem is applicable to bodies which are planar. In practice, this means the theorem applies to flat bodies whose thickness is very small as compared to the other dimensions like length and breadth or radius. The figure illustrates the theorem. According to this theorem, the sum of moment of inertia of a plane lamina about two perpendicular axes, that is x and y, shown in example axis lying in its plane is equal to its moment of inertia about an axis perpendicular to z, that is to the plane of lamina and passing through the point of intersection. I will read once again. According to this theorem, the sum of moment of inertia of a plane lamina about two mutually perpendicular axes lying in its plane is equal to its moment of inertia about the axis perpendicular to the plane of lamina and passing through the point of intersection of two axes. According to this theorem, moment of inertia about z-axis is equal to moment of inertia about x-axis plus moment of inertia of y-axis, that is Iz is equal to Ix plus Iy. Next we will take up theorem of parallel axis. According to this theorem, moment of inertia of a body about a given axis I is equal to the sum of moment of inertia of the body about axis parallel to the given axis and passing through the center of the mass of the body Ig and ma square, where m is the mass of the body and a is the perpendicular distance between the two axes. Please see the figure above. Here the given axis is I. I is the given axis and Ig is the axis passing through the center of gravity of the or center of the mass of the body. According to this theorem, I is equal to, that is moment of inertia of the body is equal to Ig plus ma square. A is the distance between the given axis I and the center of the mass. Worked example. Now we will take up some worked examples of calculating moment of inertia of bodies and worked examples on theorems of perpendicular and parallel axis. Question number 1. What is the moment of inertia of the disk about one of its diameters? Assume that the moment of inertia of the disk about an axis perpendicular to it and through its center to be mr square by 2, where m is the mass of the disk and r is the radius. Please read the question once again and I will proceed with the answer. The figure shows a planar body. An axis perpendicular to body through a point O is taken as a z-axis. Two mutually perpendicular axes lying in the plane of the body and concurrent with z-axis, that is passing through O, are taken as x-axis and y-axis. So in the plane of the body is in x-axis, shown as ox and oy. This is the plane of the body, and the body perpendicular to the plane of the body is z-axis, and all the three axes meet at the point O. By theorem of perpendicular axis, which was given in the previous slide, Iz is equal to Ix plus Iy. Now x and y are along the two diameters of the disk, and by symmetry of the moment of inertia of the disk is same about it any diameter. Hence, Ix is equal to Iy and Iz is equal to Ix plus Iy, that is Iz is equal to 2 into Ix. But we know it is given that Iz is equal to mr square by 2. Therefore, Ix is equal to Iz by 2, that is equal to mr square by 4. Thus, the moment of inertia of a disk about any of its diameter is mr square by 4. Next question. What is the moment of inertia of a rod of mass m, length L about an axis perpendicular to it through one end? Please read the question once again. What is the moment of inertia of a rod of mass m, length L about an axis perpendicular to it through one length? For the rod of mass m and length L, from the given table in the previous earlier slide, I is equal to m into L square divided by 12, where I is the moment of inertia, m is the mass, L is the length of the rod. Using parallel axis theorem, we know that I dash is equal to I plus ma square. With a is equal to L by 2, we get I dash is equal to m into L square by 12 plus m into L by 2 whole square. That simplifying, we get ml square by 3. We can check this independently, since I is the half of the moment of inertia of the rod of mass 2m and length 2l about midpoint. L dash will be equal to 2m into 4l square by 12 into half, that is equal to ml square by 3. This is the answer which was proved earlier. Question number 3. What is the moment of inertia of a ring about a tangent to the circle of the ring? Please see the diagram showing the tangent. This is the tangent and this is the ring, and R is the radius of the circle and C is the center of the circle, and diameter is also shown in the dotted line. Using parallel axis theorem, we know that I along the tangent I suffix tan is equal to I diameter plus mr square. that is equal to I diameter we know is mr square by 2 plus mr square. That is equal to 3 by 2 mr square. Hence, it is proved. Now we will take up some model questions and answers of 1 mark. Question number 1. About which axis a uniform cube will have minimum moment of inertia? Answer. The minimum amount of moment of inertia will be about an axis passing through the center of the cube and connecting the opposite corners. Question number 2. State the principle of moments of rotational equilibrium. Answer. Square root of tau should be 0. Question number 3. Find the moment of inertia of a disk of radius r and mass m about an axis in its plane at a distance r by 2 from its center. Answer. Half of mr square. This we have already solved in the theory part of this video. Can the linear momentum does not contribute to angular momentum? Answer. No. Linear momentum does not contribute to the angular momentum. It can produce only rotary motion. Question number 5. Which component of the couple acting on the rigid body produce translator motion? Radial component produces the translator motion. Question number 6. A system is in equilibrium. What can we say about its potential energy? Answer. The potential energy is minimum when the system is in stable equilibrium. Question number 7. Is radius of gyration a constant quantity? Answer. No, it changes with the position of the axis of rotation. This we have given clearly in the table of this video. Question number 8. Two solid spheres of the same mass are made of metals of different densities. Which of them has a large moment of inertia about the diameter? Answer. Sphere of small density will have large moment of inertia. Question number 9. The moment of inertia of two rotating bodies A and B are I subscript A and I subscript B, and IA is greater than IB, and their angular momenta are equal. Which one has a greater kinetic energy? Answer. We know that kinetic energy is equal to capital L square by 2I, where K is the kinetic energy, capital L is the angular momentum, and capital I is the moment of inertia. Hence, KB will be greater than KA because the moment of inertia which comes in the new denominator IA is greater than IB. Hence, KB will be greater than KA. Question number 10. A particle moves on a circular path with decreasing speed. What happens to its angular momentum? Answer. We know that angular momentum vector capital L is equal to vector R into R cross M vector V. Therefore, the magnitude of L decreases when the magnitude of L decreases, but the direction remains same. Question number 11. What is the value of instantaneous speed of a point of contact during pure rolling? The instantaneous speed of the point remains 0. Question number 12. Which physical quantity is conserved when planet revolves around the sun? Angular momentum of the planet is conserved when the planet revolves around the sun. Question number 13. What is the value of torque on the planet due to gravitational force of sun? So the value of torque is 0. Question number 14. If no external torque acts on a body, will its angular velocity be constant? No, because angular velocity is inversely proportional to torque. Hence, the external torque will not be constant. Angular velocity will not be constant. Question number 15. Why there are two propellers in a helicopter engine? It is due to conservation of angular momentum. Question number 16. A child sits stationary at one end of a long trolley, moving uniform with a speed v on a smooth horizontal floor. If the child gets up and runs about on the trolley in any manner, then what is the effect of the speed of the center of the mass of the trolley plus child system? Answer: there won't be any change in the speed of the system as no external force is working. Next we will take up model questions and answers of 2 marks. Question number 17. Show that in the absence of any external force, the velocity of the center of mass remains constant. This is a standard derivation. Please refer the link given in the description regarding center of mass. Question number 18. State the factors on which the position of center of mass of a rigid body depends. Answer. Point number 1 is it depends on the factors on which the position of center of mass of the rigid body depends is point number 1, shape of the body. Point number 2, mass distribution. So it depends on two factors. One is shape of the body and second is mass distribution. Then question number 19. What is the turning effect of the force called for? On what factor does it depend? Answer: torque. Factors. One is factors. Turning effect depends on magnitude of the force, perpendicular distance of the force vector from the axis of rotation. Next question. Question number 20. State the factors on which the moment of inertia of a body depends. So moment of inertia of a body depends on mass of the body, size and shape of the body, and mass distribution with respect to axis of rotation. And fourth factor is position and orientation of the rotational axis. Question number 21. On what factor does radius of gyration of the body depends? The radius of gyration of the body depends on the mass distribution. Question number 22. Why the speed of the whirlwind in a tornado is alarmingly high? In the whirlwind, air from the nearby regions gets concentrated in a small space. So moment of inertia is going down considerably. So I into W is equal to constant. So W will be high. Next question number 23. Can a body in equilibrium while in motion? Can a body be in equilibrium while in motion? If yes, give example. Answer is yes. The body has no linear and angular acceleration. Hence, the body in uniform straight line motion will be in equilibrium. Question number 24. There is a stick, half of which is wooden and half of it is steel. Part 1. It is pivoted at the wooden end and a force is applied at the steel end at right angles to its length. Part 2. It is pivoted at the steel end and the same force is applied at the wooden end, in which case the angular acceleration is more and why. Please read the question again and I will proceed with the answer. Answer. In the first case, that is when it is pivoted at wooden end and force is applied at the steel, moment of inertia is greater than the moment of inertia in the second case. There, because tau is tau equals I into alpha, that is tau is the torque equals moment of inertia into acceleration. Therefore, this implies that alpha in first case is less than alpha in the second case. Question number 25. An internal force cannot change the state of motion of a center of a body. How does the internal force of the brakes bring a vehicle to rest? Answer. In this case, the force which brings the vehicle to rest is friction and it is an external force. Question number 26. If Earth contracts to half of its present radius, what would be the length of the day at the equator? Please read the question. It is a hypothetical question. If Earth contracts to half of its present radius, what will be the effect of its effect on the length of the day at the equator? Answer. I1 is equal to 2 by 5 mr square. That is moment of inertia. I1 is equal to 2 by 5 mr square. So when the when the earth contracts, the radius reduces. I2 will be equal to 2 by 5 into m and r becomes half. Hence it is r by 2 whole square. That is equal to, therefore I2 will be equal to 1 by I1 by 4, because this is I2 becomes, this is I by 4, I1 by 4. Therefore, we know the angular velocity, angular momentum L is equal to I1 into omega 1, that is equal to I2 into omega 2. Therefore, I into 2 pi by T1, that is the angular velocity, omega is 2 pi by T, I into 2 pi by T1 is equal to 1 by 4 of 2 pi by T2. So that is equal to T2 is equal to T1 by 4, that is equal to 24 by 4, that is equal to 6 hours. So the length of the day will be reduced to 6 hours instead of 24 hours. Question number 27. What does a rigid body said to be, when does a rigid body said to be in equilibrium? State the necessary condition for a body to be in equilibrium. Answer. For translational equilibrium, sum of external forces should be 0. For rotational equilibrium, sum of the total torque, external torque should be 0. These are the two conditions, and based on this we have done some worked examples also. Next question. How will you distinguish between a hard-boiled egg and a raw-boiled egg, raw egg, by spinning it on the tabletop? Answer. For the same external torque, angular acceleration of the egg will be smaller than that of hard-boiled egg. Question number 29. Equal torques are applied on a cylinder and a sphere. Both have the same mass and radius. Cylinder rotates about its axis, and whereas the sphere rotates about one of its diameter. Which will acquire the greater speed and why? Please read the question once again and try to interpret it and analyze it. Answer. We know that tau torque is equal to moment of inertia into acceleration, or acceleration, angular acceleration alpha equals tau by I. Therefore, for in respect of cylinder, angular acceleration of cylinder alpha suffix c is equal to tau by IC. Similarly, in the case of sphere, alpha subscript s is equal to tau by Is. So taking ratio alpha c by alpha s is equal to inverse of, that is equal to Is by Ic because of inverse proportionality. Substituting the values of Is, we know from the standard table given, Is is equal to 2 by 5 into mr square divided by mr square. Please, for this you have to remember the tables for sphere and cylinder. That becomes 2 by 5. Therefore, alpha c by alpha s is equal to 2 by 5. Question number 30. In which condition a body lying in the gravitational field is in stable equilibrium? The body lying in the gravitational field is in stable equilibrium when the vertical line through the center of the gravity passes through the base of the body. Next question. Give the physical significance of moment of inertia. Explain the need of a flywheel. Answer. It plays the same role in rotary motion as the mass does in the translatory motion. With this, we come to the end of section 7.10. We have solved some word examples as well as model question and answers of mark 1 and mark 2. 3 marks and 5 mark questions and answers will be taken up in the subsequent videos. Next lecture will be on kinetic, rotational motion, etc. Till then, goodbye.